Hey YouTube, welcome back to my data structures in Typescript series. In this video, we're going to go over the first of multiple for heaps, and this one's going to be binary heaps. In the next following videos, we'll go over binary heaps, index binary heaps, binomial heaps, and Fibonacci heaps as well, and a few more. So very excited for this portion of the series, and let's get started. What is a binary heap? Well, a binary heap is a data structure that implements the priority queue abstract data type. So before we look at binary heaps, which is the actual implementation, let's look at the abstract data type first, which is the priority queue. A priority queue is, with the name you can guess, is quite similar to a queue. You are enqueuing and dequeuing elements into the queue, but these elements have a specific priority attached to them. So the priority that's attached to them determines the ordering of the elements, and because of that, the priority queue slightly differs from a regular queue. It does not have first in, first out ordering. The element that gets dequeued from the priority queue is the one with the highest priority. So to give you some more intuition behind the priority queue, on the left we have some operations that are called against the priority queue. So let's say we enqueue 99 and then 3 and then 50 and then -10. And then when we dequeue, instead of getting 99, which we would expect from the queue because this is the first in, first out, we get -10 because -10, in this case, our priority queue is a minimum priority queue. So the most important element you can think of is the element with the lowest priority, which is not the lowest priority, but the lowest number means it's the highest priority. So because -10 is the smallest number in our priority queue, we're going to return that first, and we get -10. And then the next one is 3, and then 50, and then 99. So you can see it's in increasing numbers because this is a minimum priority queue. And on the right, you have a conceptual picture of a priority queue. It's just kind of like a bag, and you put your priorities in, and then what you take out of it is the highest priority. So it's similar to a queue as in you're enqueuing and dequeuing elements, but there's no inherent ordering with respect to time. Where is a priority queue used? And that's a great question. Priority queue is leveraged in a few of the more advanced algorithms like Dijkstra's shortest path algorithm, as well as the minimum spanning tree algorithm, which is on the right over here. And then to give you some real-life applications, you can think of hospitals using priority queues because when patients arrive into the ER, they have to report their symptoms, and then the hospital staff will use those symptoms to determine a specific priority for that patient. So if someone has some life-threatening thing that they need to be dealt with, then they have to have a higher priority than someone who has a cough, that's going to the ER. So priority queues can be used anywhere where you need to assign some sort of priority to any elements or objects. So let's look at potential solutions and implementations when implementing the abstract data type of a priority queue. And our goal is to have constant time access and operations to popping the smallest or greatest element in the priority queue. So your first intuition might be to use an array. And here's an array of numbers, and let's say to get that constant time access, we keep a pointer to the minimum element. So if we wanted to dequeue the element that has the smallest value, we have it right there, 8. So let's go with this implementation, and let's say we dequeue and we get the value 8, which is great because we just return the value that min is pointing at. And then because we are done with 8 and we have dequeued it off the priority queue, we set that to null. But now here's the problem. We have to find the next smallest element, which is going to take a linear amount of work in the worst case. So using an array takes O of n time when dequeuing elements from the priority queue. So can we do better than this? We want to possibly achieve logarithmic or constant time. Let's try to do better. So the next idea that I'm going to present is storing the elements in a sorted list. So you have something like 1, 2, 3, 4, 5, 6, 7, 8, and when you dequeue the smallest or greatest element from the priority queue, let's say 1, this next smallest element, and let's say we're talking about a minimum priority queue, is just the next one over, right? If you had a list of 1, 2, 3, 4, we dequeue 1, and then the next element would be 2. So finding the next min/max is a constant time instead of linear. We don't have to do that search. So let's think about this solution. What if we use an array, a sorted array? Inserting will still cost O of n. So we have that constant time dequeuing, but now enqueuing is going to be a linear amount of time because we have to do a binary search to find the right location in the array, which is going to take log n of time. And then when we insert, we have to move all the later elements to the right. So if we're inserting into the middle of the array, we possibly have to move n elements to the right to shift to make room for that one specific element we're inserting. So the total enqueue operation is O of n. So dequeue is now constant, but now enqueue is linear, which we don't like. Let's say we wanted to use a linked list. Inserting, however, still costs O of n as well. We can't binary search the linked list because we cannot index into the linked list. We can't access the middle element or something. So linear search is going to cost O of n to figure out where in the linked list we have to insert our newly item that we want to give the priority queue. Inserting costs constant time, which is good, but the big O of n, the linear amount of work in the first step, dominates the entire runtime. So the entire enqueuing operation is O of n. So you can see with the strategies that have been presented, it's not the best runtimes. We are sacrificing here. We have constant time enqueuing, but linear work dequeuing. And here we have constant time dequeuing, but that comes at a sacrifice of making enqueue slower with O of n. So the solution to this, hence the video's title, are something called binary heaps. For the priority queue, which has faster enqueuing and dequeuing, is something called a binary heap. A binary heap is a data structure that implements the priority queue abstract data type with logarithmic removals and insertions. I forgot to say that here, which is really, really awesome compared to linear amount of work. A binary heap is a binary tree with only two properties. So if we have these two properties or two invariants, if these two invariants hold, then we have a binary heap. The first property that must hold is the structure property, and this means the tree must be a complete tree. We'll get that into the next slide. The second property that must hold is the order property, and nodes must be smaller or greater than all of their children, depending if it's a min or max heap. The first property, which is the structure property, talks about the structure of the tree, of the binary heap. And binary heaps must be complete trees. What a complete tree means is a tree where every row is completely filled except possibly the last row. So here on the right is a complete tree. Every row in this tree is filled up except possibly the last. So the only row that cannot be fully complete is the last row. And for the last row, all the nodes must be inserted as far as left as possible. So if we had a 6 or 9 here, then this would not be a complete binary tree. We have to insert it always to the left. And the reason why we need binary heaps to be complete trees is because complete trees give us a upper bound on the height of the tree, which is logarithmic. It's log of n. And this you'll see later on with the methods that we introduce for the binary heap, guarantee logarithmic insertions and removals, because insertions and removals, those methods, you have to traverse the tree up and down at the worst case. So because of that, we want to limit the height of the binary tree, and complete trees gives us logarithmic height, which is great. These examples are binary trees that are not complete. So they are binary in the sense that they have each node has 2 children, maximum 2 children each. But in this tree, not every row is completely filled. We have the third row, there's missing 2 children right here for 3, so this is not a complete binary tree. Here on the right, we do have every row except the last is filled, but on the last row, the nodes are not inserted to the far left as possible, so this is not a complete binary tree either. And here, of course, these are left skewed and right skewed trees, which are actually just linked lists, and these are not binary trees either. So here, we are not guaranteed logarithmic insertions and removals because the height of the binary trees are not guaranteed to be logarithmic. So if we had trees that were not complete, then operations of inserting and removing from our binary heap are now going to be O of n, which we don't want. We want logarithmic. The second property that binary heaps must hold is the order property, and that's the heap property / invariant. What this means is that every node must be smaller or greater than all of its children. So if we're dealing with a min heap and we want to dequeue elements that are the next smallest element in the heap, then the property must be that all nodes have to be smaller than all of those children. If we want max heap, then it's going to be greater. And one thing to note is that the left child does not need to be less than the right child. This is not a binary search tree. This is just a binary heap. the order of the children does not matter, only the parent-children order. So here I'm going to look for an example that the left child here, so we have a min heap, we have 30, 100 is greater than 40, but that's okay as long as it's greater than 30, then that's all we care about in terms of the children. So here you see the left child is greater than the right child. But looking at this triangle right here, 10, 15, 30, 15 is less than 30, which is not the same as 140, but that's okay. All we care about is parent-children relationship. So because we have these two properties, complete the structural order such that all trees are complete, the binary heaps, and the order property that every node is smaller or greater than all of its children, we can now insert and remove from the binary heap in logarithmic time. So now let's look into the enqueue and dequeue operations, inserting and removing from our binary heap. And we're going to look at a binary heap that's a max binary heap. So we have each node is going to be greater than all of its children. And what this gives us is the next element to be pulled off from the binary heap is the next greatest element. So that's the thing with binary heaps, is that the topmost element is the one we have constant time access to, which is the root. That one is either the smallest or biggest of the entire binary heap. So let's try to enqueue 34 into this binary heap. We're going to insert 34 into the bottom right to maintain the structure invariant. We need to maintain the complete binary tree invariant, and inserting the node to the bottom right is what keeps this invariant. It allows us to have a logarithmic height, allows us to maintain this complete binary tree invariant. But now the second invariant is violated, which is the order variant, because 5, not every node is greater than its children. 5 is not greater than 34. So we need to fix this by swapping 34 with its parent. So there's a lot of terms for this. You can call it swapping up, bubbling up, swimming up, sifting up as well. And I like to use sink and swim because those are some fun verbs to say. So because 34 in this instance, in this state of the binary tree is less than 5, we swap it up to try to fix the invariant that we violated. But now the site of damage has moved up because 34 is still greater than 33. So our order invariant for the max binary tree is violated. So we still need to fix this to maintain the order invariant. So we're going to try to swim up again. So we swim up and we swap 34 with 33, and now we're good because 34 is not greater than 35, so our order invariant has been restored. So this is now keeping the first invariant and second invariant. It satisfies those two invariants. We have a complete binary tree and we have the order invariant such that each node is greater than all of its children because this is a max binary heap. Let's say we wanted to delete or dequeue the next element with the highest priority, and since this is a max heap, this is going to be the element with the highest value, and this is always going to be the element at the top of the tree. So that gives us constant time access to those elements. But sorry, I don't want to get you confused that dequeuing is constant time, but it's just that we can peek and we can access the greatest priority element in constant time. Dequeuing is still going to be logarithmic. So the way we do this is we obviously need to dequeue the topmost element because that's the one with the highest priority in the priority queue. So the way to remove 35 is the first element is to swap the first and last element of the binary heap. So here we're swapping 35 with the last element, which is 5. And you might be asking, why the last element? Well, try to swap the topmost element 35 with any other element. Let's say we swapped it with 23, right? So imagine here, this is kind of in the way, but imagine 23, the 35 is now where 23 is right now. And then we remove 35 from the binary heap. Then there's some missing node right here, and that violates the structure property invariant of the binary heap. If we swap the first and last element, that means 35 will go as a child of 33, but we are free to remove it because it's the last element, and that does not violate our structure invariant. So that's why we swap it with the first and last element. So we swap it, and then we remove 35 from the binary heap. So you can see 5 and 35 get swapped, and then this can be like an intermediary step. 35 can be here, but then we remove it after because it's gone from our heap. It's dequeued. So now our first invariant, it holds the structure invariant such that it's a complete binary tree. But the second invariant, which is the order invariant, does not hold because each element is not greater than all of its children. 5 is not greater than 26 or 34. So now let's swim 5 down until our order invariant holds. So when you sink down, you have to swap with the child that is the greatest or smallest, depending on if it was a min or max binary heap. We swap it with 34 because 34 is greater than 26. Let's say we swapped it with 26. Then 26 would be here and then 5 would be here, right? But then if 26 was here, 26 is not greater than 34. So that's not really getting us anywhere. So the reason why we swap it with the smallest or greatest element, depending on if it's a min or max heap, is to make sure that when that child now gets promoted to a parent, then we know that parent will still hold that heap invariant, that order invariant on the other side of the tree. So now looking at 5, the site of damage has still moved down. So we still have not fulfilled the heap / order invariant because 5 is less than 33, and this is a max heap. 5 is greater than 4, which is great, but it needs to be greater than both of its elements. So we sink 5 down again. So we sink 5, so we swap it with 33, and now we stop because 5 is greater than all of its children. 5 is greater than 2, so our invariant holds again. So the first invariant, which is the order invariant, the structure invariant holds. The structure of our tree is a complete binary tree, and the second invariant holds because now we have every node is greater than all of its children. So up until now, we've been dealing with a tree representation of a heap, but in many applications and implementations of binary heaps, we use arrays to represent trees, and this is because arrays are faster when accessing elements. The reason why they're faster is because there's no nodes or pointers to dynamically allocate. We know there's an array of contiguous size in the memory, so we can index into the array. This gives us less overhead because all we're storing is really just an array, which takes less space than a full-on tree. And the way binary heaps are still trees, but they're just represented with arrays. And the way we represent that, I drew a diagram because I didn't like any of the ones I could find on the internet. We can see that this is a min binary heap. It's a complete binary tree, and every element is less than all of its children. So we have this first row, which is red, the second row is blue, and the third row is green. So just looking at the colors, we can see that the way we represent the trees is going row by row. And then for each element, if we want to index of the left child, let's say we want the index of the left child for 1, which is the root is at 0, and then the index of the left and right child have these specific formulas, which is I times 2 plus 1 for the left child and plus 2 for the right child. So if we did 0 for the root, 0 times 2 is 0, plus 1 is 1, which is the left child. And the same thing can be done for the right child as well. Here, for 8, let's try to see if it works for 50 and 39. The left child is I, which is 2 times 2, which is 4, plus 1, which is 5, so that's great, 50, and the same thing holds for the right child. You can check for yourself. If we want to traverse back up, the index of the parent is I minus 1 divided by 2. So let's say for 4, the index of the parent's 4 is this 3 node. So we take the index of 4, which is 3, minus 1, which is 2, divided by 2 is 1. And lo and behold, we have that element. So you can see, instead of following pointers and allocating dynamic memory, all we gotta do is some calculation, which is faster and has no overhead. So now going into the time complexities for a binary heap, we have our enqueue and dequeue operations. From the start of this video, we saw that we can only get one of them to be constant time and then the other had to be linear. So we can do better than those two solutions that I presented with the arrays and linked lists and get logarithmic enqueues and dequeues. The reason why the enqueuing and dequeuing operation are bounded with the logarithmic function is because the height of the binary heap is guaranteed to be log of n because complete binary trees are logarithmic. For enqueuing and dequeuing, we are sinking and swimming down, and in the worst case, we have to sink and swim throughout the entire tree, the entire height of the tree. So that's why we know that the time is log of n for enqueuing and dequeuing. Peaking, the min/max element, depending on if the heap is min or max binary heap, is constant time because we have constant access to the root. And then for this basic heap that we're talking about in this video, advanced dequeue and the contains method take a linear amount of work. So advanced queue I didn't go into, but let's say we wanted to remove a specific element. So we knew in this heap that we wanted to remove 23, we knew 23 was in this heap, we're going to have to do a linear search in the array to find that specific element and then remove it. So that's why it takes O of n time. The contains is the same logic for advanced enqueue. Let's say if I want to check, oh, does this binary heap contain, let's say, I don't know, 88? Well, we don't know because we have to look through the entire tree. So then we have to say, if this 88, is this 88, is this 88, all the way to the end. And of course, now at the end, we know there's no 88, so we return false. 88 is not contained in this binary heap, but that took a linear amount of work. In the next data structure that we'll cover, we're going to cover something called an indexed priority queue, which is a modification of the priority queue / binary heap data structure. And this gives us logarithmic advanced dequeuing, which is like removing a specific element, and constant time operation to check to see if something is contained within the heap. So that was it. That was an overview of the binary heap data structure. As a reminder, or in summary, the binary heap is an implementation for the abstract data type priority queue, and we have constant time access to the min/max element and logarithmic removals and insertions, which are really fast and awesome. So I'll see you in the next video where we'll go over the implementation for the binary heaps. See you then.